Deep in the Himalayas, where the earth touches the sky, lies the ultimate engineering challenge. This is the Yarlung, the highest major river on the planet, carving the world's deepest canyon. Here at the Great Bend, the river drops 2,000 meters in just 50 kilometers, holding a kinetic energy potential unseen anywhere else. Capturing this power requires a machine larger than anything humanity has ever built.
The mission: to construct a 60-gigawatt hydropower system, double the size of the Three Gorge Dam. But first, the remote silence of Medog County must be broken by the roar of heavy industry. Survey teams from the China Yajiang Group arrive first, mapping the treacherous terrain.
Precision is paramount. In a seismic zone this active, a single calculation error could be catastrophic. Before the dam can rise, supply lines must be forged. The mountains are cut back to create access.
Thousands of tons of rock are moved daily just to create a foothold for the workers.
A city for thousands of workers is erected in weeks, complete with power, water, and logistics hubs.
Tributaries are bridged. Every piece of equipment, from bolts to bulldozers, must cross these ravines.
The giants of construction, crawler cranes, are assembled on site to lift the impossible. The work never stops. Shifts run 24 hours a day to meet the ambitious timelines of the 14th five-year plan.
The stage is set. The $170 billion mega project officially begins its descent into the earth.
To harness the 2,000-meter drop, the river cannot just be blocked. It must be diverted. Meet the monsters of the underground. Custom-built tunnel boring machines designed to chew through Himalayan granite. These machines will carve multiple tunnels, each 20 kilometers long, bypassing the Great Bend. As the cutter head spins, it pulverizes the rock, pushing forward inch by agonizing inch.
The excavated rock, or muck, is carried out by conveyor belts to be repurposed for aggregate.
As the machine digs, it simultaneously installs precast concrete rings to stabilize the tunnel walls. In areas too steep for TBMs, traditional drill and blast methods are used. Explosives are carefully wired. This is a surgical strike against the mountain. Controlled detonations shatter the rock, clearing the path for the diversion channels. Once the dust settles, loaders rush in to clear the debris before the rock can settle.
To prevent collapse in this earthquake-prone zone, walls are sprayed with high-strength shotcrete.
Steel rock bolts are driven meters deep to anchor the unstable layers together. These tunnels will act as a bypass, allowing the riverbed to dry out for the main dam construction. Huge steel sluice gates are installed to control the flow into the diversion tunnels.
The diversion is ready. The mighty Yarlung is about to change course.
The cofferdam begins. Trucks dump tons of earth and rock to block the main river channel. Known as the closure, this high-stakes operation battles the current to seal the river off. With the final load, the river is tamed. The water is forced into the tunnels.
For the first time in history, the riverbed at the dam site lies exposed and dry.
Engineers descend onto the river floor to inspect the foundation rock.
The silt and sediment of centuries must be removed to reach solid bedrock.
Irregularities in the bedrock are chiseled away to create a flat, stable platform. Every inch of the foundation is tested. There is no room for weakness here.
High-pressure grout is injected deep into the earth to seal any fissures against water seepage.
The foundation is set. The site is prepared for the largest concrete pour in history. On the cliffs above, massive batching plants churn out specialized concrete day and night. A relentless fleet of trucks transports the mix to the cable cranes. Suspended on cables spanning the canyon, massive buckets lower the concrete to the riverbed. Ground crews guide the release. The first layer of the dam wall begins to form.
Immense vibrators are used to remove air bubbles, ensuring the concrete is dense and waterproof.
Layer by layer, the dam rises. It is built in separate blocks to allow for cooling and settling.
Hydration heat could crack the dam. Miles of cooling pipes are embedded to circulate cold water.
A skeleton of steel reinforcement provides the tensile strength needed to hold back billions of tons of water. Welding quality is checked via X-ray. The standards here exceed nuclear power plant requirements.
As months pass, the gray wall begins to dominate the natural landscape. These are the penstocks, massive steel arteries that will channel water into the turbines.
Wide enough to drive a truck through, these pipes are polished to reduce water friction. Automated welding ensuring a perfect seal. A leak here would be disastrous.
Once positioned, the penstocks are encased in concrete, becoming part of the dam's body. The spillways are shaped. These chutes will safely discharge excess water during floods.
The surface must be perfectly smooth to prevent cavitation damage from high-speed water. Unique to this region, seismic dampers are installed to absorb the shock of potential earthquakes.
Every batch of concrete is stress tested. The Yajiang Group takes no chances with safety.
The structure finally tops out, bridging the gap between the two mountain faces. A vertical cliff of man-made stone now stands where the river once ran free.
Deep underground, a cavern the size of a cathedral has been hollowed out for the Powerhouse.
Here, the heart of the 60-gigawatt system will beat.
The turbine runners, weighing hundreds of tons, arrive after a perilous journey through the mountains. Precision cranes lift the spinning heart of the generator. The clearance is measured in millimeters. It must sit perfectly in the scroll case. Once seated, the cover is bolted down. This steel beast will spin for decades. The rotor, an immense electromagnet, is lowered into the stator coil.
Miles of copper winding will convert the spinning motion into electricity.
These cables will carry the massive 60-gigawatt load to the transformers. Transformers step up the voltage for efficient long-distance transmission. The brain of the dam is built. A digital control center to monitor every sensor.
Hydraulic systems are tested. They control the speed of the turbines with split-second accuracy.
The Powerhouse is finished with clinical cleanliness to protect sensitive electronics.
Back on top, the massive steel floodgates are installed.
Powerful hydraulics will lift these gates against the crushing pressure of the reservoir.
Watertight seals are checked. Not a drop can pass until commanded.
Outside, the switchyard rises, a forest of steel towers and ceramic insulators.
Transmission lines are strung across the peaks, connecting Tibet to the coastal grid.
Brave linemen work at dizzying heights to connect the final links. Safety drills run the emergency shutdown protocols. Failure is not an option. Thousands of sensors are embedded to monitor stress, movement, and temperature. The upstream face is scrubbed clean. The reservoir is almost ready to fill.
The diversion tunnels are sealed forever. The river has only one way to go now. Up!
The temporary cofferdams are removed. The water pushes against the new wall.
Slowly, the reservoir begins to form. The water level creeps up the concrete face. Efforts are made to mitigate impact, though the ecological change is inevitable.
As the pressure builds, engineers watch the data like hawks.
The canyon transforms into a massive stillness. A new lake is born in the Himalayas.
The water reaches the intake towers. The giant is ready to wake up.
July 2030. The command is given.
Deep underwater, the gates open. The Yarlung Zangbo rushes into the penstocks.
The massive rotor begins to turn. Inertia fights against the water's power.
Speed increases. Voltage builds. The magnetic field engages.
Kinetic energy becomes electrical energy. The first gigawatt hits the grid.
The ground hums with the vibration of 60 gigawatts of raw power.
Thousands of miles away, coastal cities are powered by the water of Tibet.
The water, having done its work, returns to the riverbed, turbulent and aerated.
A test of the spillways creates a spectacular man-made waterfall.
A rainbow forms in the mist, a deceptive beauty over the sheer power. Security is tight. This is now a strategic asset of national importance. Maintenance is eternal. The battle against erosion and stress never ends.
The Yarlung Zangbo Mega Dam. A monument to human ambition.
But downstream, the flow is altered. The river's rhythm has changed forever.
For the millions downstream in India and Bangladesh, the water is now regulated by these gates.
Vital nutrient-rich sediment is trapped behind the wall, changing the agriculture downstream. The project expands. Solar farms are added to create a hybrid energy hub.
Wind, solar, and hydro combine to achieve the carbon neutrality goals of 2060. Advanced weather monitoring predicts floods, allowing the dam to manage heavy rains. Technology attempts to heal the scar, lifting aquatic life over the concrete barrier.
At night, the giant glows, a beacon of industrial prowess in the dark wilderness. The economy shifts. New towns emerge on the banks of the reservoir.
Infrastructure follows power. Rails and roads connect the once isolated region.
Managed by the China Yajiang Group,
The project sets a new benchmark for mega construction.
For the builders, it is a triumph of engineering over nature.
But the geopolitical ripples of this project will travel further than the electricity it generates.
From the first blast to the final switch, a process of immense scale and complexity.
300 billion kilowatt hours annually. Clean energy for a hungry nation. As the sun sets on the Himalayas, the Yarlung Zangbo continues its new, controlled journey.
This is how the world's largest dam was built.